Welcome, everyone. We welcome you to we thank you for joining the RecSys 2020 session on unbiased recommendation and evaluation. I'm your session chair for this session. My name is Olfa Nasraoui from the University of Louisville in Louisville, Kentucky in the USA. And again, if you have any questions for a particular presentation, we appreciate if you type your question on the WUVA agenda entry for that presentation. And then we will collect your questions from there and go ahead and answer them. And we encourage you to follow up with the speakers and continue the discussion after the session on WUVA as well. So without further ado, let's go ahead and get started with our first speaker. So the first speaker is Yoshifumi Seki from Gunosy, and he's going to be talking about a method to anonymize business metrics to publishing implicit feedback datasets.
Thank you, introduce. Hello, everyone. My name is Yoshifumi Seki, senior researcher in Gunosy. Today, I talk about a paper, a method to anonymize business metrics to publish implicit feedback datasets. First, I talk about the background of this study. Dataset publication is important for recommendation system studies. Datasets have contributed to develop recommendation systems such as movie rents and Netflix plays. However, implicit feedback datasets for commercial services are not enough. Recommendation systems have adopted in many unbiased services, so many unbiased datasets are needed. Our motivation is make it easier for commercial service to publish a dataset. There are some business risks to publishing a dataset. RIKEN confidential business metric is the most crucial risk. Thus, before publishing a dataset, researchers must get approval by a business manager. Many business managers are not specialists in machine learning or recommendation system, so the researcher should be responsible for explaining the risk and benefits. In this study, we focus on an implicit feedback dataset. Implicit feedback dataset include confidential business information and users' personal information. We have 4 contributions in this paper. First, we summarize the challenges of building and publishing a dataset from commercial services. Second, we formulate the problem on building and publishing a dataset as an optimal optimization program that seeks the sampling weight of users. Third, we apply our method to build dataset from the raw data. The raw data has more than 1 million users with 100 million interactions. Lastly, we implementation of our proposal method and the dataset built by our proposal method are public. We have achieved to persuade our business manager using this method. Thus, I talk about tasks in this paper. We only focus on the following 3 data: user behavior logs, user attributes, and article category. And our task is to publish a subset of the user behavior log, and we do not publish user attribute and article categories. We build dataset by sampling user approach. To explain this approach, we show the example that user behavior logs includes these 3 users' history. If the user behavior log are sampled directly, the consumption history of the users are missing. To keep the consumption history of users, we sampled users and collect log associated with the sampled users. We pose the following 3 challenges to publish a dataset. First challenge is to anonymize business metrics. We don't want to disclose confidential business metric. If the users are sampled uniformly, some business metric could be easily estimated. We must sample users with a non-uniform distribution. Second challenge is to maintain fairness. Recently, fairness is an important topic in machine learning. Publishing unfair dataset indirectly contributes to creating unfair machine learning models. We assume publishing a fair dataset is very important for company reputations. Third challenge is to reduce popularity bias. If the dataset is built by uniformly sampling, the items of unpopular category are less frequently sampled. We believe popularity bias is a problem in building dataset, and publisher must keep a certain amount of interaction with unpopular category items. Thus, I talk about proposal method. We formulate our task as a problem of finding the sampling weight of users. We want to anonymize our business metrics. However, formulating this challenge is impossible because it needs to enumerate all the metrics that we should anonymize. In other words, we sample users to make the distribution of datasets closer to specific distribution. This figure shows our method. We sample users according to sampling weight. To cross the target distribution, we solve optimization problem. Under this assumption, our loss function is defined here. This loss function calculated the distance between expected quick distribution and target distribution using Wasserstein distance. We also show two loss functions of second and third challenges. Each expected distribution is simply calculated using sampling weight. We find the sampling weight at which all the loss functions have small values. To achieve these goals, we minimize the sum of these loss functions. As experiment, we built a dataset from the raw data in our news delivery services. The number of users in the raw data was more than 1 million, and the number of clicks in the raw data was more than 100 million. From this raw data, we built a dataset that consisted of the behavior logs of 60,000 users. We built 8 datasets from user behavior logs. For anonymizing business metric, we adopt 2 types of target click distributions, DIP-F1 and DIP-F2. And users' attribute and category click distribution are controlled or uncontrolled. These distributions are controlled as uniformly. The dataset statistics showed in this table. DIP-F2 datasets are more sparse datasets than DIP-F1. Category controlled datasets are more sparse than uncontrolled. Thus, dataset properties are changed by sampling strategy. This figure shows that cumulative densities of the number of clicks of datasets. This result shows that we successfully controlled the click distribution of the dataset and hence the business metrics can be anonymized. This distribution is both user attribute, but categories are also controlled successfully. Please detail reason our paper. Next, we confirmed how the evaluation of our 8 dataset differed. This table shows that result of algorithm comparison. The result shows that DIP-F1 and DIP-F2 have different trend. Especially, evaluation of DIP-F1's dataset was similar to uniform. Item 2 back is best and item KNN is second. The dataset and the DIP-F2 have different results. Jui-Yang for work achieved the best performance expected both the attribute and categories are constrained, whereas item KNN achieved the best if the both are constrained. This may be because the dataset of DIP-F2 were very sparse. These results suggest that the performance of algorithms differed in how the dataset were built. In this study, we do not imply which parameter is better or worse. It is necessary to select sampling settings according to the purpose of the research, and it may be important to publish dataset with various settings, I think. Finally, I conclude our study and talk about the limitation of feature work. Implicit dataset is commercial service are important to recommendation system studies. However, publishing a dataset is difficult due to some business risks. Contrary to this importance, this difficulty has not been discussed and its solution have not been proposed. In this study, we summarize the 3 challenges and propose methods to solve these challenges. We apply our method to build dataset from our real-world mobile news delivery service. This study is first attempt to reduce business risk in publishing dataset. Limitation to future work is following. One of limitation is we do not give a theoretical guarantee if the impossibility of estimation. Providing such as impossibility is important. Other limitation is one that the study only considers the user item interactions. However, real-world service may have different type of behaviors. There are many challenges in task. However, previously researchers have not disclosed how to build a dataset and has not shared the knowledge with the community. We hope that our work will lead to more discussions of the process of building and publishing a dataset and that many datasets will be published. Thank you for listening to our presentation. Please visit our project page and use our implementation dataset. Thank you.
All right. Thank you very much for this interesting presentation. So we thank Yoshifumi, and we have time for some questions.
Yeah.
If you have a question, please go ahead and type it into the Wova app. And all right, so we have a few questions. The first question from Sangha Mitra. And the question is, at metrics, do you compute in the final data set to ensure, what metrics do you compute in the final data set to ensure fairness?
So is that the limitation? Thank you for the question. So the limitation of the presentation of time. So the fairness in detail is not so described the details. Our fairness is simple. So we consider the gender of users, only gender of users, and the data set, the sampled users in the data set is so male and female is included equally. It's just a simple methods, and we sampled uniformly we sampled data distribution of gender is so target distribution as a uniformly. So it's not investigate that fairness is achieved the data set some fairness metric using some fairness metrics. It's okay.
Thank you. Yeah, we have another question by Manel. How do you measure users' privacy?
Oh, that's a good question, and it's difficult. Privacy is very difficult problem. So, we do not. In this study, we remove any user's privacy information from dataset. For example, users attribute, gender or ages. Recently, there are some researches attacking users' privacy using users' attribute and content information. User content information, for example, Netflix prices, the Netflix dataset attacked by IMDb using IMDb dataset. So our dataset just user interaction by ID. So by user ID and item ID. So we removed from the content and the user's information. So we can't measure it user privacy, but so we try to remove the risk of the attacking users' privacy de-anonymization.
All right. We may have time for just one very quick question here. The other question is, could you show more in detail how the business risk is reduced by your method? Maybe not in as much detail.
Sorry, last question is
can you how is the business risk reduced? How is the business risk reduced?
So we think business risk is the dataset the risk of the dataset publication is leaking so business confidential information like a user's some business KPI. Using our method, the distribution of users' activity is different from original one. So this method can reduce the business risks.
All right. Okay, thank you so much. Again, if you have questions for the audience, please, the audience, continue typing your question on the WOVA app, and the speakers will be happy to answer on the WOVA app as well. So thank you so much.
Thank you.
We thank the speaker, and we're ready to go to our second speaker now. So Masahiro Sato from Fuji Xerox is going to be presenting unbiased learning for the causal effect of recommendation. Masahiro, are you ready?
Yeah.
All right, you go. Thank you.
It's sharing fine. Hi. May I start?
Yes, yeah,
okay.
Please go ahead.
Okay. Hi, my name is Masahiro Sato from Fuji Xerox. Now I'd like to talk about the unbiased learning for the causal effect of recommendation. This is the outline of my talk. First, I'll introduce what is the causal effect of recommendation and why it's important. Then I'll explain our unbiased estimator and unbiased learning. And I'll show the experiment results and summarize my talk. So from a perspective of service provider, a goal of recommender is to increase users' purchases or clicks. This results in improvement of sales and user engagement that are key measures of business values. So let's think of a common setting of recommender systems. A user receives a list of recommendations and might purchase some items. If the recommended items are purchased, we consider this is a successful recommendations. But is this true success? Think about counterfactual scenario. What would have happened if these items are not recommended? Some items could have been purchased even without recommendations. So by considering both factual and counterfactual scenarios, now we can know whether each recommendation increases sales or not. From this reasoning, we consider this is a true success of recommender. To formulate our problem setting, we introduce the concept of a causal effect. It is defined as a difference between the purchases if recommended and purchases if not recommended. So now we can reinterpret the goal of recommenders. To increase users' purchases or clicks, we need to rank items by the causal effect. So now the ideal ranking from earlier examples should look like this. However, there are two challenges for this new ranking problem. First one is unobservable nature of the causal effect. That is, to calculate the causal effect of recommendation, we need to know both YT and YC, but actually only one of them can be observed for specific user item pair. So we need to estimate the causal effect. But their second challenge, bias by confounding. Typically, both recommendation assignment and potential outcomes depend on user and item characteristics. For example, popular items are often purchased by definition, and that kind of item might be often recommended too. So under such a confounding, it is difficult to distinguish the causal effect and the natural behavior of users. So that makes a heavy bias in our estimate of the causal effect. In this work, we define the ranking metrics for the causal effect of recommendations. And we propose an IPS-based unbiased estimator of the metrics and developed an unbiased learning method based on the estimator. In the field of recommender systems and information retrieval, previous unbiased learning addressed the selection bias. They essentially predict either YT or YC and not targeting the causal effect. Other related work is a recommendation for the causal effect, but they are not addressing the bias by confounding. Okay, so the ranking metrics are generally expressed in this formula. That is the weighted average of purchase or clicks, positive feedback. Here, this rate is determined by the ranking position of items, and the rank is determined by the predicted score of the items. Various popular metrics are included in this form, such as AUC, precision, and DCG. Here, this average rank is a metric used in a pioneering work of unbiased learning, and it is proportional to the rank, similar to AUC. We redefined the ranking metric for the causal effect version by substituting the YUI with tau UI. We add C to each metric to clarify this is a causal effect version. We first construct an unbiased estimate of causal effect. Here, ZUI is an indicator of recommendation, and PUI is probability of recommendation, also called propensity. This rating method is called IPS. It essentially operates the rare events with low probability. With this estimate, we construct IPS-based estimator of the ranking metrics. However, the IPS is known to suffer from high variance. That is, if PUI or 1 minus PUI is very small, this left or right term can become very large. So we restrict the denominators by propensity capping. So now I explain about unbiased learning. So previously derived estimator is not a differentiable. So we here derive the differentiable upper bound for the causal average rank. We conduct SGD on these upper bounds underlined. So the experiment section, we experiment on a synthetic datasets. We have two settings on propensity distribution. One is the original to data. The other is personalized and secured. I'm sorry to say that there's some mistake in this setting, and I just updated experiments, and it's published in archive in a few hours. And we evaluated these 5 experiments, and we showed 2 of them by the data original setting. This is a result of a category level comparison. Each method is used to run the matrix factorization model. And here DLC is proposed method, and BLC is a biased one. This is the result in product level that has a larger number of items. We can see in both settings, our proposed DLC outperforms most baselines. Our method requires the propensity. We assume that this propensity is recorded as a recommendation logs. However, if it's not available, we need to estimate the propensity. So we investigate the dependence on an inaccurate propensity estimate. So here we can see that for the wide range of misspecification, that our DLC performs better than other baselines. So as a summary, we propose an IPS-based unbiased estimator for the causal effect version of generic ranking metric. And we developed an unbiased learning method for causal average rank that are applicable to a wide class of recommender model. For future work, learning methods for other metrics could be developed, and enhancement of unbiased estimator is possible by using W-robust. So that's all. Thank you for your attention.
All right. Thank you. So we thank Masahiro for this interesting presentation. And if there are any questions, please go ahead and type them on the Wova app, and we'll take them from there. So while the questions are coming, I guess I don't see any questions yet. I would like to ask Masahiro, what exactly was changed in the experiments that you mentioned are not in the paper, but you updated on the archive?
In a personalized setting of a data set, we set the propensity proportional to the ranking position in terms of item ranking, but that ranking is not properly ranked. So I experimented again. So okay, so the results I showed today is another setting which was correct.
All right, thank you. Thank you for pointing that out. All right. So we have a question by Eve, I guess. It's, can you expand on the confounder's point at the beginning? And is your method robust to unobserved confounders so far?
Actually, if there's a... Okay,
I'll read it again. I'll read it again. Okay, so Eve asks, can you expand on the confounders at the beginning? What is the point of, and is your method robust to unobserved confounders?
Okay, actually, the answer should be no, because if we assume that the confounder is only user and item characteristic. And I think that, but that's a very common setting in a recommend system. So, for example, if the user behaviors depend only on context, we should include the context as a confounder. But this work pursues a more simpler setting, which the only user and item is a confounder.
All right, thank you. Is your, yeah, I think we can go ahead and thank you so much. Thank you, Masahiro, for your presentation. And let the third speaker, now we welcome Yuta Saito from Tokyo Institute of Technology, and he will present doubly robust estimator for ranking metrics with post-click conversions.
Hi, can you hear me? And also, can you see my screen?
Yes.
Great. Let me start. Okay. Hello, everyone. My name is Yuta Saito, an undergrad at the Tokyo Institute of Technology, Tokyo Tech, and today I'm going to talk about my paper, W robust estimator for ranking matrix with post-click conversion. In this work, I study the offline evaluation of recommender system using click conversion, two-stage user feedback setting often observed in the kind of e-commerce recommender system. So let me now use an Amazon recommendation example as an illustrative kind of example. So now a hypothetical user is seeking a statistical machine learning book, textbook, and the user now clicks the ESL, the element of statistical learning. I think it's famous worldwide, but the click itself is not the outcome here. So what we want to maximize, or what we want to optimize is the conversion, the expected number of conversion in the recommendation interface. So we observe the conversion indicator, the outcome here at the second stage user behavior, only for the item with a click. Here the ESL book. And the important point here is that the conversion indicator for the other item, the item without a click in the same recommendation list cannot be observed to the analyst, right? So if you are the data scientist of the recommender system, you may want to recommend item with high conversion rate, high CBR to maximize revenue from users, or to maximize the expected number of conversion itself. Right? So for example, in this hypothetical top 3 recommendation interface, there are 2 recommenders, recommender A, recommender B, and you see that the recommender A is better than recommender B. It's simply because recommender A is now can be able to create a recommendation list having more conversion than the other recommender. So what we want to do in the offline evaluation is to identify which recommender is best in the sense that having maximum conversion in the future recommendation opportunity, right? So we want to do the offline evaluation. But the difficulty here is that we cannot use conversion indicators for all these item pairs. There are many missing conversions in the recommendation list because we cannot observe conversion indicator for the user item pair without a click at the first stage, right? So we have to do this kind of statistical estimation, statistical inference to do the accurate offline evaluation of the ranking performance of recommenders, right? So okay, let me now define the ground truth ranking performance here. So the ground truth ranking performance is defined by the weighted expected conversion obtained by deploying recommender system to the real system, right? So this is the ground truth ranking measure. It's now defined by using true conversion rate, which is unobserved to the analyst in the real world. And C is a ranking function, which can be, for example, average relevance position, discount cumulative gain, or you can also use record function or the precision function for the ranking function or the weighting function. But the important point here is that it is desirable or ideal to use the ground truth ranking matrix directory to identify the best recommender among many candidates, or to do the model evaluation. But calculating the ground truth ranking measure directory is actually impossible, unfortunately, because there are several challenging difficulties in the offline evaluation of recommender system, including missing sparse conversions and selection bias issue. So the first challenge is missing sparse conversion. So remember that the previous Amazon example, a user first clicks the item or the item web page, and then they decide whether they should convert or they should buy the item or not. So when a click does not happen at the first stage, then the conversion indicator, the outcome, is not observed to the analyst, meaning that we cannot use conversion indicator for user item pair without a click, right? As illustrated in this kind of figure, right? So, and also conversion indicators are often highly sparse, so we have to address the sparsity problem in the offline evaluation task, as well as in the offline learning task. Okay, so this is a missing sparse conversion. And the other challenge is the selection bias issue. So again, we can use only conversion indicator with a click in the offline evaluation task. And observed conversion data is often biased by many sources of causes, such as position bias, presentation bias, or the bias by past recommendation policy. I think many of you remember yesterday's amazing lecture keynote on the bias in interactive system, and we have to do the same thing in the offline evaluation task. we have to, for example, address the kind of distributional shift between the clicked events and the unclicked events to do the accurate inference for the accuracy of the recommender system for the whole population, for the whole user item pair. Right, so in summary, what we want to do in the offline evaluation is to statistically estimate the ground truth ranking measure, which is now defined by using ground truth conversion rate, PCBR. So we want to, construct an accurate estimator for the ground truth, but using only accessible information in the offline environment. And what is accessible in offline environment is the set of conversion indicators, now denoted as YUI, which is a binary random variable. But we can observe conversion indicator for user item pair with a click. And the ZUI is another binary random variable representing whether the item is clicked by user U or not. So this is the source of offline evaluation we can use in the offline environment. A previous famous solution, a popular solution for this offline evaluation is the IPS estimator, the inverse propensity score estimator, originally proposed in causal inference. So this estimator proposed in previous RecSys paper. The previous RecSys paper proposed to use this estimator to estimate the ground truth ranking measure using only bias implicit feedback. But this kind of estimator can be easily extended to our two-stage user feedback setting. And this is the definition of the IPS, which uses only click data, but it weights the observed conversion data by using the inverse of the CTL, P6A here. The CTL is the probability of an item I being clicked by user U in the ROC data. And by doing this inverse CTL weighting, we can easily prove that the IPS estimator is now unbiased for the ground truth ranking metric, what we want to estimate here. So it's fantastic. But the problem here is that the variance of the IPS estimator can be huge, especially when conversion indicators are highly sparse, which is a general phenomena, general situation in application, recommended system application. So the main motivation in this study, in this paper, is to alleviate the variance issue of the previous unbiased IPS estimator. So for this purpose, we propose the doubly robust estimator for the ground truth ranking measure using two-stage user feedback setting for the first time in the literature. So this is the definition of the doubly robust estimator. And you may think that it's kind of a bit of complex than the IPS estimator, but basic idea behind the doubly robust is fairly simple. It uses the estimated CBR, p-hat CBR, to impute the missing conversion information for user item pair without a click. The IPS estimator does not use any information of the missing conversion, for example, user item pair without a click. But the doubly robust estimator uses the estimated CBR to impute the information of the missing data. And by doing this imputation technique, the doubly robust estimator is at first unbiased for the ground truth. This is the same property as the previous IPS estimator. But the fascinating feature with this estimator is that in most cases, this estimator has a lower variance than the previous unbiased estimator. This result is remarkable because it enables, using doubly robust enables us to accurately estimate the ground truth ranking performance, say, the ability of recommenders to obtain as many conversions as possible accurately, even if the conversion indicators are highly sparse, which is a general setting in recommender system. That this is the result of the variance reduction as shown in our theoretical analysis. Right, so this is the main theoretical and methodological result. Let's use doubly robust to estimate the ground truth ranking performance of recommenders using quick conversion two-stage user feedback. So finally, let me now introduce some experimental results just briefly due to the time constraint. But the important takeaway message is that the doubly robust estimator outperforms the other estimators, including the naive and the IPS estimator. The naive estimator is the biased estimator, and the IPS estimator is the unbiased but has high variance due to the sparse conversions. So the doubly robust estimator always outperform the other estimators in the evaluation task. The ground truth ranking performance is now DCZ or recall. So this result means that we can do the accurate offline model selection, offline model evaluation of the ranking performance of our recommenders by using our proposed doubly robust estimation. So in conclusion, we studied the offline evaluation of ranking performance of recommenders using possibly biased, possibly sparse click conversion two-stage user feedback data. And previous unbiased estimator has a large variance, so it is unbiased. because of the highly sparsity problem. And we propose a doubly robust alternative to estimate the ground truth more efficiently, and propose estimator evaluates the performance of arbitrary candidate recommenders accurately in our real-world experiment. Okay, that's it. Thank you for listening. And please refer to our paper if you're interested in details, including theoretical analysis, interesting semi-synthetic experiment, and also we discussed related work in our paper. Okay, that's it. And I'm now happy to take some great questions.
All right. Thank you for your presentation. Thank you, Yuta. We have a question. And again, the audience, we're welcome to type your question in the WOVA app, and we'll pick them from there. So we have a question by Sangamitra. The question is, how is clicked versus not clicked recommendation used in the system?
Okay, thank you for the question. So, okay, it depends on the estimator you use. For example, the previous unbiased estimator uses only clicked data, the observed conversion data to estimate the ground truth ranking performance because it's simply easy. But our doubly robust estimator uses, also the non-click data. The doubly robust estimator first estimates the expected conversion rate, P hat CBL, using observed conversion data. And by doing this estimation beforehand of the evaluation, the doubly robust estimator also uses the non-click data to reduce the variance. So it depends on the estimator, I think.
All right, thank you. So we have another question did you use explicit or implicit feedback? And the question asked, since you used the root mean square error in the evaluation, this is the reason why Sami is asking, did you use explicit or implicit feedback?
Okay, I think it's a question about my experimental part. So in my real-world experiment, I used explicit feedback data to synthetically generate the click conversion situation. So the relative RMSE is not the RMSE for the recommended prediction. The RSME in my slide means that the mean scale error between the ground truth and the estimated ranking performance. So the RSME measures the accuracy of the estimators. So this is not the accuracy for the prediction. So if you're interested in detail in the experimental part, please refer to my paper, maybe section 5, section 6. But yeah, thank you for the clarification.
All right, thank you for that.
Yeah, so it's not a standard, It's not a standard recommended evaluation because our purpose is to propose the new evaluation metric or new evaluation estimator.
Okay, so we have another question. How did you evaluate the unbiasedness of the estimator? This is by Sami is asking, how did you evaluate the unbiasedness of the estimator?
Oh, okay. It's a theoretical result. So unbiased, okay. So we can theoretically calculate the unbiasedness so the ground truth is our estimate. So by taking the expectation of our estimator, and then and if the expectation of an estimator is equal to the estimate, then we can say that the estimator is unbiased. So it's a theoretical result, and we can calculate and check whether the estimator is unbiased or biased.
All right, thank you. Another question asked by Allegra, where are the probabilities coming from? Are they real? That means they're logged, or are you estimating them?
Okay, thank you for the question. And in the real-world experiment, we estimated the propensity score, which is the CTL, using log data. And actually, in my paper, I discussed how to estimate the propensity to use the IPS estimator or to doubly robust estimator. So if you're interested in the estimation method of the CTL, please refer to our paper. Maybe I remember it's discussed in our section 4. So yeah, I discussed the point in our paper. And in the real-world experiment, I estimated the CTL using matrix factorization method.
Okay, we have another question. In case of an actual, this is by Shanth, asks, in case of actual search engine, this does not have conversion, it has only click. then how would you estimate how would the doubly robust estimator work in that case?
Okay, thank you for the great question. It's okay. The answer is it's open problem. So the basic motivation behind our work is that it's difficult to use doubly robust estimation only when we do not have the conversion data. So when we have only click data, then we cannot use the doubly robust. We can do only IPS. But the contribution of our paper is that if we have the quick conversion two stages of feedback, then we can use the doubly robust, right? So how to reduce the variance of the estimation when we have only quick data is an interesting future research direction, I think. But thank you for the great, interesting question.
All right, thank you for that answer. We have some time. So Allegra asks again, can you expand on how these applications of the IPS and the doubly robust estimator and recommender systems differ from standard applications in causal inference?
Yes, method is similar to causal inference, but the motivation is a bit different. Our motivation is to, refine the distributional difference between clicked and non-clicked events. So we do not aim to, estimate the causal effect of recommenders. So the motivation is a bit different, but the methodology is very similar. So one possible future research direction is how to, combine the doubly robust estimation and the causal-based recommenders in a, theoretically refined way.
All right. So thank you for that. Thank you, Yuta. So the next speaker, right? So we welcome the next speaker is Bowen Yuan from National Taiwan University. And Bowen is going to present unbiased ad click prediction for position-aware advertising systems.
Okay, can you hear me?
Yes, we can.
Okay. Hello, everyone. I'm Yuan Bowen from National Taiwan University. Today, I'll present our latest work, Unbiased Ad Click Prediction for Position-Aware Advertising System. This work was done in collaboration with Yaxu, Zhang, Zhenhua, and Professor Lin Zhiren. And in this work, we focus on ad systems. In a typical scenario of an ad system, we assume we have n ads and k precisions. So for each request, an ad system retrieves k ads and place them to the k precisions. We give a simple example as follows, where we have 5 ads and 3 precisions. So we retrieve 3 ads and place them to the 3 precisions of display. Some of them are clicked by users, and the goal of ad system is to maximize the revenue from clicks on this display ads. In this work, we will consider the position-aware scenario. That is, an ad placed in various positions has a different click probability. To maximize the revenue for each request, the system displays a k events with a maximum sum of expected revenue, which is computed by the bid of this ad. And it is the price of this ad paid by the advertiser if the ad is clicked by users. And we time the times the click probability. And the click probability is precision dependent, so we call it precision or CTR. However, choosing the k events from the P and K permutations costly when n so large. So to have the efficient display algorithm, we assume for each event, its precisional CTR can be expressed as a non-precisional CTR P tilde ij times a same probability beta k. And with this assumption, the top k events can be efficiently chosen as follows. We first retrieve the top k ads according to the non-precisional CTR times a bit. Then we place the retrieve the k ads from the first position to the kth position, where we number the positions according to their beta values. And now we need to estimate the non-precisional CTR. However, for most systems, as we do not know if an ad is seen or not, so the observation from the non-precisional CTR and the same probability cannot be collected. So we have no training labels for estimating the non-precisional CTR. Instead, we have the training labels for estimating the positional CTR because we have the position-dependent click information on past display events. So the core problem is how to estimate the non-positional CTR from the position-dependent labels. And to accomplish this, the existing approach first learn a positional model. We call it a Jui model, model Jui from the click information on parsed displayed events as an estimation of the positional or CTR. And then we extract a non-positional model F to give a prediction of this non-positional CTR, just as a following example. However, in this work, we argue the non-positional model F obtained in this way may be heavily biased. Record that the existing approach first learn a positional model Jui on the parsed display events. We point out that the learned positional model Jui is biased only if the following displayed distribution is uniform. That indicates a parsed displayed events were uniformly chosen. However, a practical system tends to display events with higher expected revenue. So the selection bias occurs in learning the positional model Jui, and the non-positional model F extracted from this biased positional model Jui is also biased. Additionally, suppose we have addressed the issue of the selection bias, and now we have a unbiased positional model. We call it a G-star model. And from this G-star model, we expect to extract unbiased non-positional model F-star as follows. And we expect this F-star model can give unbiased estimation of the non-positional CTR. However, the extract model can be shifted by a constant, arbitrary constant C. And clearly, the top K as retrieved by this shifted model times the bit are not the same as those by the ground truth F-star model times the bit. So now let me introduce our solution. We start from addressing the selection bias caused by the non-uniformly displaying. And the simple way is to collect the training set by uniformly displaying events. However, it causes significant loss of the revenue. Instead, our idea here is to consider non-displayed events to simulate a scenario where all events can be displayed, so that the selection bias can be addressed. For precision-aware system, the non-displayed events include the events of non-retrieved ads. Recall the examples. And the ad 3 and ad 4 were not retrieved. So their events colored by blue belong to the first type, non-displayed events. And the second type are events of retrieved ads with non-placed positions. In these examples, ad 1 was retrieved in the position 2, but for position 1 and position 3, the ad 1 with these 2 positions, the events of ad 1 with position 1 and position 3 belong to the second type. We color them by the yellow. And by considering all events, the click information can form a dense binary tensor as follows. And with this tensor, we propose to directly learn the non-positional model F by solving the following fully labeled problem. And we prove the resulting non-positional model can give unbiased estimation of position-independent CTR, which equals to alpha times the non-positional CTR. And because the alpha is a constant for all events, the top K as retrieved by the position-independent CTR times the bit are the same as is chosen by the non-positional CTR times the bit. Okay, however, for non-display events, their labels and the clicks and all clicks on this non-display events are unobservable. So we have no labels for non-display events. So we apply counterfactual learning techniques. They first collect the small but unbiased subset through the uniformly displaying. And then we learn a model A from the unbiased subset to impute labels for any non-displayed events. And by following W-robust method, we're solving the following unbiased problem, where for displayed events, their loss terms are weighted by the propensity scores. And for non-display events, we use the imputed labels to compute their loss terms. Okay, next I will present our experiment. For each data set, we generate a training set as follows. We first do the display event generation by the following 3 versions. The first one is biased one, and where the events are not uniformly displayed according to their expected revenue. The second one is unbiased one, where the events are uniformly displayed. The third one is the combination of a biased data set, of a small ratio of a biased data set and a large ratio of a biased data set. We do the label generations we directly generate the precision-dependent clicks and all clicks as labels for displayed events. Besides of both settings, we also consider an ideal setting where we directly use unbiased events generations, and their labels have been already precision-independent click and all clicks. For the test set, we applied the ideal setting on different time window to have this test set. We compare the following approaches. First one is Grady. It is the existing approach, which learns a precisional model G from the biased data set, and we extract the non-precisional model from it to give the final predictions. And the second one is random. It learns a model from the unbiased data set. The third one is a CF. It learns the model by the Cont'd learning framework, where we use a small ratio of unbiased data set to train an imputation model to impute labels for non-displayed events, and we solve the problem based on W-robust method. The last one is ideal. It directly learns the model from the ideal setting. Its performance is considered as upper boundary results. The experimental results are as follows. We first say the Grady performs the worst, and the reason is that due to the selection bias, learned precisional model G is biased. The extracted non-precisional model is also biased and gives poor predictions. Now let's move to ideal and random. They perform the best. And the good performance of ideal is reasonable because it directly learns from the precision-independent labels. However, for random, it's learned from the precision-dependent labels, but we can see by addressing the selection bias, the non-precisional model F learned from the precision-dependent label still can give unbiased estimation of the precision-independent CTRs. And next, we see a CF by considering the non-display event, CF performs significantly better than Grady. And in contrast to random, where we need a large unbiased data set, CF only needs a small ratio of data for the uniform display. It is practically useful. And finally, I will conclude this work. In this work, we first argued the non-precisional model F obtained by existing approach gave the bias estimation of non-precisional CTR, because we first point out the issue of the selection bias, and next we show even if the learned precisional model is unbiased, the extract non-precisional model can still be biased. And to handle these issues, we derived a novel counterfactual learning framework to directly learn the non-precisional model F. And we proved the resulting model F can give unbiased estimation of the precision-independent CTR, and the top K as chosen by the precision-independent CTR times the bit is same as expected ones by the non-precisional CTR times the bit. Okay, that's all. Thank you.
All right. Thank you for the interesting presentation, Bowen. I think we have time maybe for one question. So we have a question by Sangha Mitra. Is a small set of users exposed to random items for data collection?
Yes, we use a small ratio for the randomizations.
Right. Okay, so I have actually one more question. So in your experimentation, did you look at the revenue, like the impact on revenue, like with either like the debiased versus the biased strategy?
Sorry, I don't get.
Like, is there any proxy to the revenue other than the click through and so on? I mean, how does that? How is the revenue impacted right, for this approach?
If I understand correctly, you mean the revenue from my approach and
yeah. So you mentioned before that obviously sometimes debiasing an approach can reduce the revenue, right? For most of the
yes
based methods, right? So how do you think this approach, is it guaranteed to kind of maybe increase the revenue, or is there a sacrifice sometimes?
Okay, and so if I understand correctly, because we use a small ratio of randomizations to collect unbiased data set, is cause a loss of revenue. But this ratio can be controlled by small ratios, and we can balance the randomizations cost, and we expect the unbiased prediction can earn more revenues and the loss of the loss on the randomizations. Yes.
All right, thank you. So if there are any more questions, the audience is welcome to please type them in the Wova app, and you can continue the discussion after this. So thank you, Bowen, for the great presentation. And we're going to our fifth paper right now, which is on reproducibility. So Ju-Sun from Macquarie University is going to present, are we evaluating rigorously benchmarking recommendation for reproducible evaluation and fair comparison?
Yeah. Hello, Olfa, can you hear me?
Yes.
Thanks for your introduction. My name is Ju-Sun, and currently I'm a lecturer at Macquarie University, Australia. Today, I'm very glad to present our research paper, Are we evaluating rigorously? So I will go through the following 5 parts. Recent decades have witnessed the great prosperity of recommender systems in both academia and industry, and they have been widely studied and applied in various domains, such as the e-commerce, the point of interest, and the multimedia. So with tremendous amount of the recommendation algorithms being proposed, one critical issue has attracted much attention. There are no effective benchmarks for evaluation. This consequently leads to 2 major concerns: unreproducible evaluation and unfair comparison. Different from other domains like the computer vision, where mature benchmarks are available for evaluation, while benchmarking recommendation is challenging in 2 aspects. First, we have a lot of data sets from different platforms. For example, in the movie domain, we have Movie Lines, Netflix, Amazon Movies, etc. And even for the same data set, we may have various versions. For example, we have Movie Lines 100K, 1 million, 10 million, and so on. And besides, different papers may adopt different data processing strategies, data splitting methods, evaluation metrics, and parameter sightings. And most importantly, majority of the papers do not report details on data processing and parameter sightings, which leads to inconsistent results in reproduction by different researchers. So these issues motivate us to investigate the evaluation rigorousness in recommendation. As a starting point, we focus on top-end recommendation task, which is one of the most important tasks in recommendation. To this end, we systematically review 85 papers for implicit feedback-based top-end recommendation, which were published in the recent 3 years on 8 top-tier conferences. And we summarize essential factors related to evaluation, such as utilize the data set and data splitting method, evaluation metrics, and parameter tuning strategies, and so on. And through a holistic empirical study, we comprehensively analyze the influence of different factors on the final recommendation performance. And based on the results, we create benchmarks by proposing standardized procedures and provide the performance of state-of-the-arts. Besides, we also released the Python toolkit named as Nasraoui for rigorous evaluation. So in summary, our work shed light on the urgent issues of rigorousness in evaluation for recommendation and lays foundations for future investigation. And first, and let's talk about the paper collections. As we mentioned, we review papers published in the recent 3 years on 8 top-tier conferences. we focus on method for the implicit feedback-based token recommendation. To this end, we searched the accepted full paper list for the 8 conferences in the 3 years, and we consider papers with titles containing the keywords recommend or collaborative filtering. Finally, we manually select the papers that adopt ranking metrics such as precision, recall, NDCG to evaluate the performance of the recommendation. So this figure here shows the distribution of the paper collection. Based on the paper collections, we do comprehensively analysis. And first, we analyze the utilized data set. And overall, there are 65 different data sets utilized in the 85 papers. And the figure shows the top 15 most popular utilized data set in the paper collection. And we conduct a careful selection to choose 6 data sets by considering their popularity, the domain diversity, authority, and information richness of the data source. And in terms of the data pre-processing, we find that around 15% of the paper adopt pre-processing strategies, and among them, more than 16% use 5 or 10 filter settings, and others adopt some other settings. So besides the original setting, we also consider the 5 and 10 filter settings by following the majority. The table here shows the statistics of the data set we utilized in our experiments. And the comparison baselines varies a lot in different papers. And the figure here shows the top 10 most widely compared baselines. And we carefully select 7 baselines, which covers different types of recommendation algorithms. And there are 2 types of objective functions utilized in those papers, pointwise and the pairwise one. And around 15% of the papers adopt the pointwise objective functions, while around 14% adopt the pairwise. So in our study, we compared the effectiveness of both pointwise and pairwise with different types of loss functions. And also we find that around 17% of the collected papers consider the unobserved feedback as the negative samples when designing the objective functions. While it is not practical to leverage all unobserved feedbacks, therefore negative sampling is adopted to balance the efficiency and the effectiveness. And in our study, we compare 3 different types of samplers, uniform, low popularity, and high popularity. And regarding the data splitting method, we find that around 16% of the papers adopt split by ratio. That means they will maybe adopt 18% of the data as the training site and the rest at the test site. While we also find that different papers may adopt different proportions. Some adopt 18%, while others maybe adopt 15, 16, 17, or 19, and so on. And they may split the user-item interactions at the global level or the user level. And some of them consider the 10-step information when they dividing the data, while others do not. We also find that around 13% of the papers they adopt leave one out. So in our study, we adopted the split by ratio and set the proportions being 18%. We split the data at the global level by considering the 10-step information. And in terms of the evaluation metrics, the figure shows the distribution of the top 10 most popular utilized evaluation metrics, and we adopted the top 6, and among them, four metrics measure whether a test item is present in the top recommendation list, while the other 2 accounts for the ranking predictions of the test items. One of the most important factors is the hyperparameter tuning. And in terms of validation strategy, we find that around 14% of the paper directly tune the hyperparameters based on the performance on the test site. And in fact, an extra validation site should be returned from the training site to help tune the hyperparameters, which is called nested validation. Therefore, in our study, we consider the nested validation by returning 10% of the training site at the validation site. And for the search strategy, we adopt the efficient Bayesian optimization method. And here is our experiment results. Due to the time limitation, I don't present the details. So I just show several interesting findings by our study. So first of all, we find that the recommendation performance does not necessarily improve with denser data sets. And also pairwise log loss generally outperforms other types. And uniform samplers, though simple, performs better than the popularity-based sampler. And the baselines with random aware split by ratio outperforms those with time-aware split by ratio. Finally, the best hyperparameter sightings for one specific metric does not necessarily guarantee optimals with respect to other metrics. As I mentioned, we also released a Python toolkit, which is named as Nasraoui, with the goal of performing rigorous evaluation in the recommendation. And our toolkit is still keeping updated and maintained. And for the to benchmark the evaluations based on our empirical study, we proposed the standard procedures in terms of the data set selections, the proposings, the baseline comparisons, the objective functions, and data splitting method. Also, the most important one, hyperparameter tunings, and the availability of the code and data set. And so you may refer to our papers for more details. And also with the goal of providing a better reference for fair comparison, we also report the performance of 7 baselines across the 6 evaluation metrics on the 6 data set under different settings. So you can refer to our gate for more comprehensive results. So finally, let's conclude our paper. So we aim to benchmark recommendation for reproducible evaluation and fair comparison. To this end, we systematically review 18 recommendation papers and conduct extensive empirical study to analyze different effectors on the final recommendation performance. Based on this, we create benchmarks and release a Python toolkit for rigorous evaluation. And for our future work, we plan to consider more deep learning-based baselines and more diverse recommendation tasks, such as the session aware. So that's all for this presentation. Thanks for your attention.
All right, thank you so much. Thank you, Zhu-san, for this excellent presentation. So we have some time for some questions. The first question by Sami is, how did you treat the unobserved items in the training?
Sorry.
Sorry, can you hear me? Yeah.
Oh, yeah, I hear you, yeah. Unobserved items in the training.
Yes, so how did you treat the unobserved items in the training?
Yeah, so in our study, because it's just the starting point, so we follow majority of papers, we treat the unobserved items as the negative items. So based on these items, we will adopt the different sampler strategies to sample the unobserved items.
All right, thank you. Another question asked here by Vineeth. What are the features of the software package, i.e. the Python package that you're proposing, and do they consist of algorithms or metrics? And what about data sets?
I mean, the feature of the software package.
Yeah.
Okay, so in our development implementations, we use Python 3 and we use the most popular deep learning frameworks, PyTorch. And also you can check with our gate for more details because our second author is mainly focused on taking charge of the implementation. So if you have any further questions about the implementations, you can send me email. I can forward it to the second author to give you a clear and comprehensive answers for that. Yeah.
All right. Thank you. So we have another question by Semi, and the question is, when you state that time splitting strategy is worse than the leave one out strategy, do you mean in terms of how the model can generalize for unseen data?
The time splitting strategy. Actually, in our study, because this is really a huge, work. But in our current study, we only consider the split by ratio, time-aware split by ratio. We haven't conducted experiments with respect to the leave one out. So leave one out is our future work. We are just, conducting experiments with that. So we don't have any conclusions about the performance in terms of split by ratio and leave one out. Yeah.
All right. Thank you. So we have a question by Himan. He asks, out of curiosity, did you perform your analysis on different versions on machine learning data sets? If so, did you observe a discrepancy in performance?
Analyze different versions of
on the movie lens, sorry, on the different versions of the movie lens data set. Sorry, my bad. ML, yeah. So different versions of the moving lens, and if so, did you observe a discrepancy in the performance?
Okay, I think this is a very good question because we really have a lot of different versions for movie lens. Because the time limitation, we cannot do such a comprehensive comparison. So for the movie lens data set, we just select the most widely used movie lens data sets, movie lens 1 million. Actually, when we implement, we test our platform, we compare with the performance with movie lens 100K because it's a smaller data set and it's very easy to to tune parameters. But we really never compare the other movie lens data sets. I think this is also one of our future work. A lot of things to do, with our future work. Yeah,
I'm sure. Thank you. All right, so thank you, Jui-san. We appreciate taking the time for answering all the questions. So the last speaker is an industry paper by Zhenhua from Huawei Noah's Ark Lab, and he's gonna present counterfactual learning for recommender systems.
Okay, can you hear me?
Yes, we can.
Okay. Hello, everyone. I'm Zhenhua Dong. Today's topic is about counterfactual learning for recommender system. Here are our collaborators from Huawei and Renmin University. Firstly, I will briefly introduce the counterfactual learning. UDPO defined the letter of causality with 3 layers. The first layer, association. It learns association with observed data without considering the causality and unobserved data. Most of current machine learning applications belong to this layer. Intervention is the second layer. It can actively take action with plans. It can explore new logic and causality for making better decisions. Counterfactual is the final layer. It can learn the unobserved world with the imagination and counterfactual inference. It has a chance to create new things. It's maybe one way to strong AI. Let's see the machine learning community. Southern had a course named the Counterfactual Machine Learning. There are mainly 2 topics, model the world and model the bears. For model the world, it studies how to use the partial information data to train a full information model. It also studied how to use the offline data to evaluate the online metrics. There are so many bears, so it studied how to use the counterfactual model to handle the bears. More than half of the course is about the evaluation and learning problem in recommendation system, information retrieval, and advertisement system, because their challenges, their bears challenges are significant. Let's see 2 important bears. The first one is position bears. Position bears describe the tendency of the user to interact with items on top of a list with higher probability, regardless the item's actual relevance. Let's see one example. Document 4 is relevant, but document 4 rank on the first place. The user maybe they have less chance to see it, so the user can't click it. Another important bias is selection bias. Selection bias occurs when the study population is not representative of the target population. Let's see the example. The previous recommendation model didn't expose the document 4, so the user can't see it, although the document 4 is also relevant. How to handle it? Let's see the counterfactual recommendation system technology. Firstly, let's see one interesting question. What kinds of data can be used to learn an unbiased model? Here is my answer. Uniformly expose every item to every user in every context, and let each user to give his or her preference. As we know, we have a lot of candidates, so it is impossible in real world. but it is possible in counterfactual world. UD4 defined counterfactual as a probabilistic answer to what would happen if. I will introduce full counterfactual learning technology for recommendation system based on 3 kinds of data: biased observed data, unbiased observed data, and unobserved data. Let's see our first approach, counterfactual data learning, also named the direct method. That method can learn imputation model with observed samples and predict the labels of unobserved samples. Here is the loss function. There are 2 terms. The first term is regular term. W is our recommendation model. The second term, L hat means all the samples, including the observed samples and unobserved samples. Here, the label, we use the imputed label from the imputation model. There are 2 challenges for direct method. The first one, the imputation model is very hard to learn. The second one, high complexity to train with all the samples together. How to handle it? We designed the counterfactual data learning framework. Firstly, we use the uniform data to train our imputation model. Here, the uniform data means we expose items to users randomly. With the imputation model, we can impute the unobserved samples label, and then we combine the displayed samples and non-displayed samples together. We efficiently learn with the block coordinate descent plus conjugate gradient method to reduce the complexity. After that, we can train our recommendation model, such as CTR model. Let's see our experiment results. With 1% uniform data, our proposed counterfactual method are better than the baseline method. As we know, the uniform data is very expensive. So we also tried the smaller uniform data. Our method are also better. Okay, let's see our second approach, correct the biased observed samples. IPS method is most popular method belong to this approach. Propensity score is defined as the conditional probability of receiving the treatment given pre-treatment covariance. Here is the loss function, where L means the observed data. Each observed sample divides the propensity score. The propensity score method have challenges in recommendation scenario since the number of candidates is huge in recommendation system. The first one is overlapping assumption is very hard to satisfy because not all the candidates have chance to be exposed. The second one, the small prediction error for propensity will lead a big model error. How to handle it? We try to use the inference function. Here is the definition of inf function. It traces a model's prediction through the learning algorithm and back to its training data, thereby identifying training points most responsible for given prediction. Here is the formula to compute the inference of a sample J in training side to a sample I in a validation side. Our idea is very simple. We use the uniform data as the validation side, and we compute each sample in the inference of each sample in the training data, and we use the inference function as the weight. Here is the formula to compute each sample's weight. Phi is the inference function. And with this reweighting method, our proposed method are better than baseline method. The detailed information can be found in our SCAR work. Okay, the third approach named the doubly robust method. It combines the IPS method and the direct method together. As I introduced, the IPS method is very hard to do. Propensity score is hard to learn in our recommendation scenario. So here we use a hyperparameter to adjust the observed samples and the non-observed samples. And then we use BCG plus CG method to efficiently train all the samples together. Okay, let's see our last approach, joint learning with unbiased data and biased data together. We do a pilot study with our advertisement system data. We train 2 logistic models. The first one, we train LR model with the only non-uniform data. The second logistic model, we train our LR model with both uniform data and non-uniform data. In terms of AUC and ECPM, our combined LR model are better in terms of AUC, ECPM. Okay, the pilot study inspired us to try some advanced method to use our unbiased data. So we designed a general knowledge distillation framework via uniform data. There are 4 kinds of approach. The first one, model distillation. Model distillation is the traditional knowledge distillation method. We share the model structure trained from the uniform data. The uniform data is a teacher. The second one, feature distillation. We learn stable features, stable samples from the uniform data. The third one, label distillation. We learn imputation model with unbiased data, then adjust the biased data. The last one, sample distillation. We jointly learn the biased data and the unbiased data together, just the causal embedding method in RecSys 2018. The detailed information also can be found in our cigar work this year. Okay, that is conclusion. Today, I introduce 4 kinds of method for counterfactual recommendation system. What's the next? I think causality is very important. As we know, the current industry recommendation system train complexity models with huge number of samples, high-dimensional features. It works in some degree, but are we on the best road? For example, I decide to watch a movie tonight just because a friend Bowen told me it's a good movie for me. My friend told me it's a causal feature. So I think the future recommendation system need to understand the people's decision mechanism and find the most important causal features. It's very hard, but it's valuable to explore. Okay, thank you for your listening, and thanks my mentor, Professor Zhang. I think he would be happy to see my first work in present in RecSys. Thank you so much.
All right. Thank you for the presentation. We have some time to ask some questions to Zhenhua. So we have a question by Sammy, which is the hyperparameters used to replace the propensity? Does the hyperparameter introduce extra bias? And is the model still unbiased as a result of this? If you could explain.
So the question is the hyperparameter used to replace the propensity introduce actual balance. Is the model still unbiased? Oh, it's a very good question. I didn't think about that question. Oh, okay, but it's a great question. Yeah. So I will think about it later, and I will answer it on the Hua when I have some idea.
All right. Thank you. We have another question by Vineeth. He asks, how do you evaluate the counterfactual recommendations since we don't have ground truth? Did you do some form of A/B testing or human evaluation of the counterfactual recommendations?
Yeah, that is a very good question. As we know, most of current data sets, such as Mueller data, they are biased data set. But fortunately, we also have some unbiased data set, such as Yahoo R3 code data set, just like Yuta introduced. We also use the 2 kinds of data set. And in our product, we also expose a 1%. We also expose uniformly to the items to the users. So we are lucky we have the uniform data. We can use the uniform data as our validation data set. So the uniform data is unbiased. So I think uniform data is quite important for the counterfactual studies.
All right. Thank you. We have another question asked by Sean. Is biased or unbiased data used for model evaluation?
Yeah. As I just answered, the unbiased data is the golden data. It's golden standard. we need to use the unbiased data to do the counterfactual learning research. Yeah.
All right. Sammy asks another question. Causality can be tricky due to the lack of data. What do you suggest on how to generate unbiased causal data?
Unbiased causal data. Yeah, just I introduced. I will give two examples. One example, in our CTR system, we just expose randomly. We give chance to the items. All the items have the chance to be exposed. As we know, propensity score have the assumption, overlapping assumption. Every item had to be chance to expose. That's the first example for CTR system. Another system is Yahoo R3. As we know, people would like to read the movie music they like, but we need to ask a user to read all the movies, all the music they listened, they watched. Yahoo R3 is one that kind of decide. So with that method, we can get the uniform unbiased causal data set. Yeah.
All right. So we can take maybe 1 more minute since we started a little bit late. Allegra asks, can you help me understand how the probabilities for a deterministic recommendation model are not always unity?
Oh, it's a very good question. As we know, the deterministic recommendation model, they have a pairs model bias. We also call it the selection bias. For example, one item, the user like the item, but the pairs model don't expose the item, so the user don't have chance to observe it. So the previous model have the selection bias. Yeah, I think that's one example to answer your question.
All right. If you have just a few seconds to ask, Chih-Jen asks how to use the unobserved data if it's not observed.
Oh, yeah, it's a very interesting question. That is the counterfactual learning. Why we call it counterfactual? What would happen if? Here, we use the uniform data to train the imputation model. And with the imputation model, we can impute the label of unobserved samples. As we know, we know the X, we know the features, but we don't know the label in recommendation system because we can assume the user see the item. We get the user's feature, the item feature, the context feature, but we don't know the label. So we need to use the imputation model to learn the label for the unobserved data. So we have label Y, we have the feature vector X. We can build the unobserved samples. Yeah.
All right. Thank you for that. And we thank the speakers. We thank all the speakers for their presentations, for the very interesting presentations. And the audience is encouraged to continue the discussions and asking questions on the WOVA app. And we encourage you to go for the social events in between and the next sessions. And I have a clapping sound here. Okay. So thank you very much.
Thank you.
So that brings us to the end of the session. Thank you all for coming. Thanks to the audience.